Hello everyone and welcome to the Monday stream. Today we're going to be doing another programming challenge, and this time we're going to be diving into something that's a little more mathematically heavy than other stuff that we've done before. In the last challenge we did Dijkstra's algorithm, which was that had a lot of math in it. It used graph theory, but this is going to use a lot more hardcore math, in the sense that the math is much more directly input into the actual algorithm than with Dijkstra's algorithm. So what is RSA encryption? So RSA encryption is an asymmetric key encryption algorithm that allows you to encrypt and decrypt data, and so you can send it securely, so that you can transmit data across the internet securely. That's how HTTPS works. So yeah, why is it so secure? Well, this is probably the most secure encryption algorithm in the world, and it's so secure because of that asymmetric aspect of it. So asymmetric means that the keys for encrypting and decrypting are different. So in this diagram here, you see that with the plain text, you encrypt it using a public key, something called a public key, and then you get a ciphertext, and then you decrypt it using something different called a private key. So those two keys are not the same, but they are related. They are entirely related to each other. So this is in contrast to symmetric key encryption, which is something like AES, where you have to use the same key to encrypt and decrypt the text. So a simple example that you might understand better is with the mailbox. So anyone can put stuff in it. You can put bombs in there. You can put anything. Anybody has access to put stuff into your mailbox. That's something like the public key. But only you have your mail key. Only you have access to the private key. So that's why it's so secure, because one key cannot be used to both encrypt and decrypt. So yeah, a little more conceptual understanding of RSA. So it's based off of a mathematical concept called a one-way function. So one-way function is something that is easy to build up, but is not easy to break down. So let's say you multiply two numbers together, that's building it up, and then you want to break it down by finding those two factors. That's actually what we do here, and you might not think that is too hard, but the numbers that we will use are very carefully selected so that factoring is very, very difficult. And the factors that we will use are going to be randomly generated large prime numbers, and these prime numbers are hundreds of digits long, and they usually equate to whatever the key size is. So it's 128 bits, 1056 bits, stuff like that. So yeah, that's essentially why it's so secure. So let's go through the basic. So what we're going to do in this stream is we're going to go through the algorithm with a pen and paper. Well, for me, OneNote, and then after that, we'll actually implement it in Python, and I'll explain why I'm choosing Python in a sec, or once we get through this. All right. So let me get the. All right, pen is working. Okay. So the algorithm works like this. So the first step is key generation. So key generation. So the first step is we want to generate two numbers. Generate two prime numbers, P and Q. Just like that. We want to go ahead and then with that calculate n, or calculate the RSA modulus. That's what this number is called, the RSA modulus. n, which is equal to p times q. So n in this algorithm is what links the two keys together. So the principle is you're going to use p and q to determine the public and private keys themselves, and n will be that linking factor between them. N will be a part of both the public and private keys, but because it's a one-way function, if you have one of them, if you have one key, it's going to be super hard to find the other key. It's not going to really work out that well. All right. So you calculate the RSA modulus, and then you need to calculate something called the Euclidean totient. So calculate totient, which is denoted as phi of n, the Greek letter phi of n, which is equal to p minus 1 times q minus 1. The fourth step is to determine e. So select e, which is such that e is relatively prime with the totient, and it's less than the totient. And 1 is less than e, which is less than or equal to the totient. Just like that. All right, then the fifth step will be calculate d. I need to hold on a second. Just let me move I need to organize my desk a little bit. You want to calculate d such that calculate d, which is going to be the modular multiplicative inverse of e with respect to the totient. So modular multiplicative inverse of e over the totient. And we'll go over how to calculate that with pen and paper first, and then I'll show you guys the algorithm that we use to do it in code. All right. Yeah, so then E is going to be your private key, and E is going to be your public key. It's going to be the key that you use to encrypt data, and D will be the private key, the stuff that you use to decrypt data. So that's the whole point about anyone can send you encrypted stuff, but they can't decrypt it, and only you can decrypt it with your private key. All right, so let's start this right now. Let me actually just copy let me go ahead and start inserting some spaces here. All right, that should be good. All right, so first thing we'll do is we will just calculate P and Q, or generate P and Q. For now, we'll just be doing smaller prime numbers, so it's easier to calculate. But like I said, in industry standards is to have these P and Q as hundreds of digits long. So P, let's say, is equal to 11, and Q is equal to 13, just like that. Okay. Next thing we want to do is calculate the RSA modulus. Let me just select this. I'm writing slanted for some reason, so that's why I wasn't able to select it. Okay, so N is equal to 11 times 13, which is equal to 143. I need to write that better. Let me actually just keep track of the important values over here. All right. Bring all this back up here. So calculate N is just the product of the two, as the product of the two numbers. P and Q. Next, we want to calculate the totient. So the totient is just equal to p minus 1 times q minus 1, so it's going to be 10 times 12, which is equal to 120, so that is 120 over there. And now we want to select E such that E is relatively prime to phi of n and it's less than phi of n. So relatively prime means that it shares no common denominators, so the greatest common denominator between E and phi of n is 1. So that's, right now it's just going to be the prime numbers, so I'll list a couple. So 7, 11, 13, 17, and dot dot dot. But you see that none of these numbers here share a common factor with 120, which is phi of n, apart from 1. So we'll just select 13 out of this, and E will now equal 13. Okay. Now this is going to be a bit more math heavy, but we're going to calculate D, which is the modular multiplicative inverse of E over phi of n. So what does this mean? This means that this statement here just equates to E times D mod phi of n is equal to 1. And we're going to have to use something called the extended Euclidean I think I just said something wrong. Euclidean algorithm to solve this out. So if you look up extended Euclidean algorithm, it's going to be broken down into 2 steps. So the first step 1, will just be the basic Euclidean algorithm. Algorithm, yeah. That looks really wrong, but alright, I'm just going to erase that. Alright, so the Euclidean algorithm. And if you look it up, if you look this up, you'll look at an equation that's something like ax plus by is equal to 1. In our case, we're going to replace a with 120, so a is going to equal, so it's going to be phi of n x plus b will be e y, don't mistake that for the natural base, is equal to 1. And we can break this down to 120 x plus 13 y is equal to 1. And this equation here will translate into 120 is equal to something times 13 plus a constant. So this is where the modular aspect comes into it. But essentially what we're trying to do is we take these two numbers, put the 120 on the left side, the 13 on the right side, and we want to figure out how many times 13 goes into 120 using integer division, so floor division. That just means we don't care about the decimal place. We just want to get just the integer number of times that 13 goes into 120. So it's going to turn out to be 9. And then we just add the remainder to balance out the equation. So that is just plus 9 times 13 is 117. So plus a 3. Oh my god, my dog. Alright, I'll be right back. Oh god. Okay, sorry about that. So this is the first step in the Euclidean algorithm. We translate this equation into this x plus y equation into this equation here. Yes, dog. Okay. So next thing we want to do, here, let me actually just label a couple things. So this 13 goes there. The 120 goes there. This number is how many, I miswrote, how many times 13 goes into 120, or in Python terms, 120 floor division of 13. And then the 3 is just a balancing constant. Alright, next step in this is we're not actually going to solve this because we would just get 120 is equal to 120, but that's not the purpose of this equation. The purpose of this is to now take the 13, bring it over to the left, so the 13 goes there. Put the 3 now over here. The 3 gets brought down. And we need to do the same process. So how many times does 3 go into 13? It goes in 4 times. And then you just add a 1 to balance out the equation. And once you get to a 1 over here, you can just stop. So once constant is equal to 1, stop. And what you will get is that 1 is the greatest common denominator of the, well, this isn't the greatest common denominator right now, but the entire Euclidean algorithm would stop when the constant is equal to 0. So if we did continue this, a 3 would equal to something times 1, and it's just 3 plus 0. But for the RSA purposes, we just want to stop when the constant is equal to 1. And you would find that this 1 is the greatest common denominator. Yes, yes, I know, dog. You can go down if you want. Okay. Oh, where are you going? All right, see you. All right, so that's where we are right now. But oh my God! Stop barking! Oh my God, this dog! All right. Oh my God, this stupid dog. Alright. So you stop, for our purposes, we're going to stop when that constant is equal to 1. And we want that constant to be 1 because we want these numbers to be co-prime, which is, once again, means that the greatest common denominator is 1 between the two. They share no common denominators or factors apart from 1. Alright, so that's the first part of the extended Euclidean algorithm. And the second step is going to be something called back substitution. Back substitution. And we're essentially going to go backwards in order to find our D in relation to E. Okay, so the way we're going to do this is we're essentially going to rearrange this bottom equation so that we put 1 on the left. So if 1 is on the left, that means that if we subtract 4 times 3 from both sides, we get 1 is equal to 13 minus 4 times 3. Alright, and then we're going to keep going. So next we're going to substitute in whatever 3 was based on the second equation here. So so 1 now is equal to 13 minus 4 times what is 3? That 3 is 120 minus 9 times 13, just like that. And I just got that from this equation over here. So let me just actually draw a line. 3 is equal to 120 minus 9 times 13. 1 is equal to 13 minus 4 times 3, just like that. And once you get this factor, and once you get back to the top, we're going to get our answer. So you essentially just combine like terms. So 1 is equal to, how many factors of 13 do we have? So we have 1 here, and then a negative 4 times a negative 9 is plus 36. So 37 times 13, and then minus 4 times 120. Just like that. And this is going to be our E. So once you have E in the combining like terms equation, you stop there. And the coefficient in front of the E is your D. So our decryption key, D, is equal to 37. So yeah, that is essentially how you calculate D in there. So D is equal to 37. So that's how you determine the keys. And now once we have the keys, we can actually go into encryption and decryption. So encryption, we just use this formula. So the numerical value, or what we're going to use, is something called the ASCII value. So the code of each character in the cipher is going to equal to the code of each character in the message. So M to the power of E, which is our key, modulus N. Sorry, mod N, just like that. And then the decryption will be D, or this time, when we decrypt, we're going to get the message out. So M is equal to C to the D mod N, just like that. Okay. So you can see how this would be difficult to reverse, essentially. So let's actually just go into an example. So let's say that we had the text hi, just like that. I can't write, so don't worry about that. So what is this in ASCII codes? Let me go to. All right. So H, capital H, is 72, and lowercase I is 105. So it becomes 72, 105, just like that. So when we encrypt, we're going to get C is equal to, C at 1 or 0 is equal to 72 to the 13 mod N, which is 143. And I don't have my calculator. Well, I actually do have a calculator. Hold on. Programming. What? Where's my didn't I did this in Python. Hold on. Math EQN. Alright, so pi eqn.py equation is going to be 72 to the 13 modulus 143, and we should get a 7 out of that. This is equal to 7, and then a C at 1, so the second character in the cipher is going to equal 105 to the 13, and then mod 143, and this is going to equal so let's do the same thing. I'm just using a calculator that I built, that we actually built in JavaScript, using the shunting yard algorithm. So 105 to the 13 modulus 143. What? I think something's wrong. Modulus 143. Alright, there we go. 50. I don't know why it wasn't working. Alright. What was it? Sorry, I forgot. It was 58. Okay. Alright, so now that we have the cipher is equal to 7, 58, we now want to decrypt it. So message at 0 is going to equal the cipher, so 7 to the D, which is 37, so 7 to the 37 modulus 143. And let me just do that out once again. 7 to the 37 modulus 143, and we get a 117. We shouldn't get that, but I think I did my math wrong. Okay, well, anyway, I probably did my math wrong. Unless I... Modulus 143. Alright, I think I did my math wrong. Okay. But anyway, you should get back the same number. It probably just can't handle that large power, 7 to the 37. But yeah, so you should get back the same number, 72 and then 105. And then you can convert that back to the text when you're ready with that. Okay, so that is... Let me actually just write down the timestamp. Hold on. Get a pen out. All right. We have been for 2552. Okay, now let's get into the code. All right, so back there, I can get rid of that. I can get rid of my drawing tablet for now. All right, let's get into this. Okay. All right, so using our example, we are going to just do all this in a main method. So def main takes nothing, and then we'll just do main. Let's just go ahead and print out hello RSA just to make sure everything works. We'll do pi RSA. Alright, all works there. Okay. Alright, so let's just do this right now. We'll do key generation after. That'll take a bit of explaining to do as well. Alright, so we have P is equal to, what did I say? P is equal to 11. Q is equal to 13. N is equal to P times Q. Phi of N is equal to P minus 1. I can't type. Times Q minus 1. Just like that. I don't care about... Oh, alright. That's phi of N. Next, we're going to select a value for E. And all we'll do is we'll say for for E in range, and we'll do 1 to 5n, and we'll actually let's just say we'll just say E is whatever we had it as 13. So E is equal to 13, but we'll actually have to randomly generate it when we get into the actual algorithm, because it'll be really the numbers will be really large, so you can't just iterate through every single one of them. Alright, so E is equal to 13. Next we want to say D is equal to modular inverse, so we'll put a function up top, def modular inverse of A with respect to B, and we'll just do a pass for now. D is equal to modular inverse of A of E and phi n. And then next we want to have the message is equal to hello world, or yeah, let's just do hello world, or RSA for now. We'll have a method up top to encrypt, so def encrypt message, or let's pass an E, N, and then message, because so our public key, I may not have explained this, but our public key is a combination of both E and N, and the private key will be a combination of both D and N, because we needed both to calculate the values. So because it's M to the E modulus N, and then C to the D modulus N. So you need both, or you need 2 of the 3 factors. Alright, so encrypt We'll just have a pass for now. And then we'll need a decrypt method as well. So def decrypt D, N, and then cipher. I hope that's how you spell cipher. Is it? Let me check. Alright, that is how you spell it, with an I. Okay. So encrypted is equal to encrypt E and message, and then decrypt is equal to D and encrypted, and then we'll just print everything out. So print, we'll say the message, G, print F, we'll say, let's do E, D, and then N, just for the purposes here. And then we'll print the encrypted value. So encrypted, and then the decrypted value. Just like that. Okay. Alright, so let's actually write in some of these functions here. So in the modular inverse, we'll have to call a function called extended greatest common denominator. Def EGCD, and that'll be of A and B. And we'll just do pass for now. So modular inverse, what we're going to do is EGCD will return a GCD, then X, then Y is equal to EGCD of A and B. So you can, so what will happen is, where am I going? Why is this? What is going on? All right, there we go. So the modular inverse, the extended GCD algorithm will return the greatest common denominator, and then two values, 37 and I believe -4, if I'm correct, will be the second value that it returns. We can check on that. So that'll return 3 values in total. And if had this factor of 37 been negative, all we would do is just add, we would just add the totient back to it. So all we would do is, so if x is less than 0, x plus equals m, and then we just return x, just like that. Okay. So yeah, that's the modular inverse function, and now let's write the EGCD function. And this is going to be, I'm just going to write out code first, and then we'll go through the debugging and see how, and we'll see how it works. All right. All right. So we'll need 6 variables to start. So s is equal to 0, old s is equal to 1. T is equal to 1, old t is equal to 0, r is equal to b, old r is equal to a, and then while r does not equal 0, so you can kind of see that parallel. Oh, what's going on? What's going on? Okay, so you can kind of see this parallel. So while r, which will end up being the greatest common denominator, while r does not equal 0, we want to iterate through this. So the quotient is equal to old r and then floor division with r. So that is determining this factor here, the 9 and then the 4. Then old r and r is going to equal r comma old r minus quotient times r. So you can kind of see how this is the remainder, so this is the balancing constant, and this is just the coefficient in there that we want, and then we'll need So we could determine the greatest common denominator with just R and old R. But because we want to do backtracking, back substitution, we'll need to store two other variables which will allow us to do so. So the old S, old T, and S and T, those variables will allow us to actually do the back substitution. So old S is equal to S. So we're essentially just putting S in old S, and then we're doing the same thing that we did with the R. So old S minus quotient times R. And then old T is equal to T, old T minus quotient times T. Make sure the second one is an S, not an R. Okay, and then we want to return three things, so we'll return old R, old S, and old T. And this will be the return GCD and then X and Y, just like that. So yeah, let's actually just test this out. Well, let's just write the encryption algorithm too. All right, so for the encryption, all we're gonna do is so we'll go through each character, and like I said, so the cipher is equal to an empty string, and we'll end up returning the cipher. I, not a Y. And so we're going to iterate through each character. So for C in message, we want to get the value of that. So let's say M is equal to ord C. So this returns the value for C for the character. And then next we're going to want to actually raise that to the power. So thankfully Python has a fast modular power or modular exponentiation function. So we don't have to write it ourselves, but in other languages we would. So all we're going to do is just say cipher is equal to a string. So we just want to convert the result to a string of pow. We're going to pass in M, E, and N. So that equates to the M to the E modulus N. And we just want to add a space after that. Just like that. Because this is how we'll separate the different elements, and that's our encryption function. And the decryption function, all we're going to do is we'll have a message. So message is equal to nothing now, and then we'll return message. So parts is equal to, so we'll need to split this up into parts based on the spaces because we encrypted each character separately. So cipher dot split, and that just splits it across a space or white space. Then we initialize message, and now we want to go through the parts. So for part in parts, we're going to say if part just to make sure it actually has something, and then all we're going to do is we're going to get we will say C is equal to, so the cipher value is equal to the integer value of the part. So that just converts the text, the number in the string to an integer. And what we're going to do is we're going to say message plus equals, and then we're going to convert a result to a string. So we're going to do the modular exponentiation again. So pow of, it's going to be C, D, N, and then we're going to add a space, or no space, sorry. Just that, and then return message. And we should be all good to go. Let me just go ahead and make sure this all works. So name N is not defined. Oh, it's capital N. That's my mistake. Yeah, make sure you have your variables named properly, or else you'll get those errors. All right, CLS. Hmm. 13 and 37 is what we got. So the modular inverse is working. 143 is also what we want. Encrypted is something weird though. Why is it? This is what? What is going on? We got all the numbers right, but encrypt. What do we? That's weird. Let me just print out each character just to make sure we're getting something. Yeah, it's giving us stuff. Oh, cipher. Oh, you need to add it. I'm an idiot. Cipher plus equals. I didn't get much sleep last night. Oh, great. All right, 7, which is what we got. Which is good, 7 and 58. But this is not right. Let me just go ahead and make sure that this is splitting it up right. So print part. Yeah, it's splitting it up right. Decrypt, and we want, well, 72 is that. Oh, you know why? Because we don't convert it back. Aha. So we don't want to add this string. We want to add the char value. So CHR. Now it should work. Aha! It works. Okay, that's all right. So we did it. Make sure you're using the right functions, not All right, so yeah, that is practically it. That's the basic side of it. Now we're going to actually have to get into some more complicated generation of. Yeah, that's the basic part. The generation is the part that's going to be hard. Okay. Alright, yeah, so that's basic RSA. Now let's move into key generation. And like I said, this is going to be large prime numbers. And alright, so this is going to be kind of difficult. So let's go ahead and do let's have a variable called key size is equal to, let's just do a power of 232 for now. We're going to have a function at the top that will just return keys. So let me just make sure I'm getting this right. Alright, def generate keys, and we'll do key size, and default is 1024. I think that's industry standard to have it as 1024 bits, which is a lot. And we'll just return or pass for now. And what we'll do here is we're going to erase all this, and we're going to say EDN is equal to generate keys key size. Just like that. Alright, key size itself will need several methods. It'll need modular inverse, it'll need, which we already defined, it'll need another method called generate large prime. And that'll take key size is equal to 1020, or just key size for now. We'll need a function to determine if it's co-prime. So def is co-prime P and Q. This will allow us to determine if our candidate for E is co-prime. Then we'll need a GCD method because the co-prime relies on GCD. So def GCD, and that'll be of P and Q. This will be using that same Euclidean algorithm that we did, and then this is going to be the meat of it. So we're gonna have two methods. One is called def is prime. That'll be of n, And then the last method is going to be something called rabin-miller, or miller-rabin. This is going to be, these are primality test algorithms, and it's kind of complex to think about. And I will post a link to one of the explanations that I found pretty helpful. So it'll just be rabin-miller N and D, and pass for now, and then we'll just need a couple of imports, or we just need random, and that is it. Okay, so yeah, we'll just need random for this case. Okay, let's start with the easiest and we'll move up. Alright, so GCD first. I'm not going to explain this much, it's not too important, but this is the Euclidean algorithm. A Euclidean algorithm to find GCD of P and Q. All it is just say while Q, PQ is equal to Q, and then P modulus Q, and then return P. I'm not going to explain that because we kind of worked through that a little over here a little, but that's not the point of this video. So that's GCD. Next we'll want is co-prime, so that's simply just to say if the greatest common denominator, hold on, so returns true if GCD of P and Q is 1, so relatively prime. And all we're going to say is return GCD of P and Q is equal to 1. That's just a Boolean statement there. And then next we'll need generate large prime and generate keys. So the generate large prime, this will be pretty self-explanatory. So so all it'll do is just return random large prime number of key size, bits, and size. So all this is going to be is num is equal, so while true, because we want to test random candidates just to tell if they're prime. So num is equal to random.rand range. So we want to go from key size -1 to key size. So let me explain why. So let's say our key size is equal to 4. The maximum value for a key would be 1, 1, 1, 1, which is 8 plus 4 plus 2 plus 1, 15, yeah, 15. So that'll be the maximum size. And the minimum would be 0, 1, wait. Minimum would be 1, 0, 0, 0. Just like that, because the key size must be of that size. It can't be less, it can't be greater. So when we want to find a random number, we essentially just want to go from whatever this number is, which is 2 to the 3rd, so 8 to 15. And what you're going to get is that's from 2 to the 4 minus 1 to 2 to the 4 minus 1 there. But the 4 in the minimum, the -1 is in the exponent, but in the maximum, the -1 is in the actual expression, not in the exponent. All right. So what we're going to say is random range includes the endpoint. Okay. So 2, and we're going to use a Python power operator. So 2 and then 2 asterisks. Asterisks. What is that, the plural of asterisks? I don't know. Yes, it is. Asterisks, and then we want to do 2 to the key size -1. Just like that, and then we want to go all the way up to 2 to the key size and that whole thing minus 1, just like that. And then we just want to determine if is prime num, return num. So that you might think that this will be inefficient, but it's necessary if we want to have the level of security that we do want. Okay, so that's generate large prime, and now we're going to go ahead and generate the keys. Alright, so we'll initialize E, D, and N to 0, and at the end we will return E, D, N, just like that. Okay, so we want to, first step is get prime numbers P and Q. So P is equal to generate large prime key size, and then Q is equal to generate large prime at key size as well. N is equal to P times Q, so this is our RSA modulus. Phi of N is equal to P minus 1 times Q minus 1, and this is our totient. Next we want to choose E. E is co-prime with phi n, and 1 is less than E, is less than or equal to phi n. So what we're going to do again is we're just going to get a random E. If we were using smaller numbers, we could just iterate through each number up to from 1 to phi of n, but because these numbers are going to be hundreds of digits long, it's not going to be worth it. It's going to be that would be very taxing on the computer. So all we're going to do is just say while true, just do E is equal to random.rand range, and we're going to do the same thing that we did above. So it's going to be 2 to the key size minus 1, and then 2 to the key size, and then that whole thing minus 1. Let me just make sure I did that. Yeah. And then we just want to check if is co-prime E and phi of n, return or break, because we've determined what E is. Alright, so that's break. And then next we just want to say choose D. D is mod inverse of E with respect to phi of n, and this just says, let me get the equation. E times D mod phi of n is equal to 1. What is... There's a truck outside my house that's just... I have no clue what it's doing. Hopefully it doesn't mess up the audio too much. Alright, so D is equal to that. And all we're going to say is D is equal to modular inverse of E with respect to phi of n. Just like that. And yeah. So that's the generation stage. And now we want to get into the test. So I'll start with a simple prime test, and then I'll go to the rabin-miller test, which will be more complex. So this will just be return true if n prime. What is going on? And this method will fall back to rabin-miller if uncertain. So this method is here to prove wrong. So to prove that the number is not prime, not to prove that it is prime, because that's kind of difficult to prove that it is prime. So all we're going to do is... So the first condition will be 0, 1, negative numbers not prime. So if n is less than 2, return false. Next, we're going to want to say low prime numbers to save time. And we're going to create a list, low primes, and that's going to be equal to an array. And let me actually just get that because it's I have it on my GitHub. I'll put this link on I'll put this link on the video as well, because this just has all the prime numbers from 0 to 1000. No, why did it paste that? Why did it paste that? Oh, it did paste it right. Okay. All right. No, it didn't. No. Oh, I know why. Because it. Okay. All right. Low primes is equal to that. We're going to want to see if in low primes. So, if n in low primes, return true. So this is the one step where we can prove if it's prime, but that's not really a proof. Next, we want to say if low primes divide into n. So as the numbers get bigger, the chance that these prime numbers will be a factor of that, will be in part of the prime factorization of that, is going to be likely. So all we're going to say is if for prime in low primes, and we're going to say if n modulus prime is equal to 0. So if n divides by prime cleanly, then we're just going to return false because it's proved it wrong. If it has a factor other than 1, then it's a composite number. All right. Now, this is going to be starting into miller-rabin, and I'm not going to explain much of it, but I will just go through some of this. So this miller-rabin is kind of difficult to think about. Let me here we go. Wait, is this right? Yeah. Okay, yeah. Okay. So yeah, the corner case is there, blah, blah, blah. And then we're going to want to iterate. So essentially what we're going to want to do is we're going to pass in a number, d, which it's kind of hard to explain. But there's a good explanation back here. So there are important things that have helped prove the miller-rabin algorithm. So one of them is that Fermat's theorem. So that if n is a prime number, then for every a, 1 is less than or equal to a to n, then a to the n minus 1 modulus n is equal to 1. So yeah, that's kind of that's one of the I'm sorry, this is one of the things that stumped me a lot. Here, let me actually just write the code, and then I'll try and explain it. All right, so the first thing we want to do is find number, let's say number C, yes, C, such that C times 2 to the R is equal to n minus 1. D or C is equal to, and we're going to start it as n minus 1. And because we know that C is not, or n is not even because it doesn't divide by 2, so we'll know that C even because n not divisible by 2. And then we want to make D odd, essentially. So while C modular 2 is equal to 0, so while C even, we want to say C divided by equal 2, so we're just going to make C odd. And then this C value we're going to pass into the rabin-miller algorithm. So we'll try and prove not prime 128 times. And what we're going to say is for I in range of 128, we're going to say if not rabin-miller, and we're going to pass in n and c, then we're going to return false. So if rabin-miller returns false, then we know it's false. Then it is definite that this is false. Rabin-miller has proved that n is not prime. Let me just make this a c. Return, and rabin-miller will return true. Sorry, it'll return true if it's is likely prime. So if rabin-miller returns false, it's automatically not prime because one of these conditions was proved as not prime. So yeah. All right, now so that is the entire is prime function. Now let's get into the rabin-miller. So we're going to have a number. A is equal to random.rand range between 2 and n minus 2 minus 2. Hold on, let me make sure I'm doing this right. So the random number wants to be between 2 and n minus 2. Corner case and make sure that n is greater than 4. So we can, okay. Yeah, so it'll just be, no, this is fine right here. Okay. So we want to have a number a, and we're going to say x is equal to the power of a, d, n, so the modular exponentiation. So this is equal to a to the d modular n. Next we want to see if x is equal to 1 or x is equal to n minus 1. We're going to return true. So if x is equal to 1, then we know it's a prime number, or it's likely a prime number, or if it's equal to n minus 1, then it's also likely a prime number. Okay. And this is based on, let me get the statement, this thing right here. So a to the n minus 1 modular n is equal to 1, just like that. And we're essentially just going to keep doing that iteratively until d is equal to n minus 1. So square x. So all we're going to say is while d or c does not equal. You know, let me just make this a d for now. I wanted to avoid confusion, but that's how this site says it. So I'll just keep it for now. So c is not equal to, or d does not equal n minus 1. We're going to say x is equal to pow. So we're going to do some more modular exponentiation. So x to n. We're going to multiply d by 2. And we know that d, when we multiply d by 2 enough times, it will get to n minus 1 because that's what we determined over here. Because d, in these three lines right here, we initialized d as n minus 1, and then we divided it by 2 many, many times. So if we multiply it by 2 the same number of times, we'll get back to n minus 1 there. So this loop will end. And then we essentially want to have the same conditions, but if x is equal to 1, we know that this number is false, or this number is not prime, it's a composite. And otherwise, x is equal to n minus 1, return true. Wait. I said it wrong. This function will return false if it's likely not prime. Did I say that right? Oh, it's likely not prime. It's not. Oh, no, we know it's not prime. I'm sorry. Because, once again, if you're using Fermat's theorem, we know that if it doesn't satisfy this condition here, so a to the n minus 1 is not equal to n minus 1, then it doesn't really work out. So yeah, that is rabin-miller, and now let's generate our key size of 32, and we'll see what. I hope this works. Oh, nice. Oh, yeah, I put a colon there for some reason. Okay. ADN. What did I do? Let me make sure that pass an ND. Or maybe this has to be that. Third argument not allowed unless all arguments are integers. So we know D is an integer, so maybe I just have to convert this to an integer. Yeah, that's probably it. What? Oh, you know, let me just do this quickly. So A is going to be equal to 2 plus random.randint. Let me. And we'll do, you know what, get rid of the 2 plus. This is just going to equal 2 to the n minus 2 minus 2, just like that. God damn it. So is D not an integer? That's weird. Let me just try. X plus equals m. Now we have problems with our. Why did I add m? What is m? All right, now this is just syntax. X plus equals b. My mistake. Aha. Okay. There we go. So you can see that now that we have longer keys, this would be really difficult to do by hand. So that's why the computer is super good at it. And this is essentially it. Unless we can also well, let's print out P and Q just to make sure that they are prime. Let me just go ahead and print. Just like that. Alright, so P is equal to this number, and let's get into a prime tester. Prime number tester. Is this number prime? I think I broke the website. I definitely broke the website. That's a big number. That might be bigger than the largest inch. Yeah, I think that's why. Oh, here we go. Is it prime? Okay. And then the second one was Q. What? I don't know. And we'll do, and that's a prime. Okay. Nice. Nice. Yeah, so that is RSA encryption. Pretty neat. Yeah, that's it. I don't have anything else for you guys, but I will end off with one note. This method can get inefficient and or vulnerable if you're passing in text all the time. Because if you see, when we pass in hello, there were two of the same numbers, so you could use frequency analysis to do this. But because it is standard in the industry to only use RSA to encrypt AES keys, because AES is a much more efficient encryption method, RSA is used to encrypt AES keys. Frequency analysis is irrelevant because AES keys are randomly generated. And when they're used in combination, I actually built an app like that where I use both of them in combination. It is very powerful because if you have, well, like I said, AES is more efficient than RSA. So the RSA will be used to encrypt an AES key, and as a result, both the client and the server can have access to that secure AES key without ever having it being vulnerable. So stuff like this isn't used to encrypt text or like messages, or it's not used to encrypt files. AES is used to encrypt files across network communications, and RSA is just used to decrypt the AES key with it. So yeah, that is fun stuff. Yeah, that's pretty much all I have for you guys today. Where did the... There we go. I'm done. Yeah. Alright, I will... I'm done. Alright, I'll see you guys maybe later this week. I don't know. I might want to put a... I wanted to continue with the OpenGL stuff, but I never got around to it over the weekend. So I might do that later this week. Who knows? But yeah, I will see you guys. Yeah. Then. Bye.